Welcome, big dogs. Today we're talking shock response spectrum, why it's useful for a structural analyst, and actually demo how to derive this curve in Python. So an SRS curve basically shows the response acceleration versus the natural frequency of a single degree of freedom system. In practice, you have multi-degree of freedom systems, but it's just not practical to run a shock analysis on a multi-degree of freedom system and get results quickly. It's very tedious, very time consuming, and designers they always want answers like now. I mean, it's insane. If you can't give them answers now, they're going to outrun you, and that could be catastrophic in the end, because if they make design changes that don't satisfy the shock requirements, guess what? It's just wasted work. So an SR curve allows you to get a acceleration response in terms of G's, where you can run a G-load analysis in an FEA program and get an answer quickly. This is just all you need to do for preliminary design phase. Now, once you get to the end, then you do your full-fledged shock analysis. But at the beginning, it's just more practical to do it this way with an SRS curve. So what it allows you to do is you pick the natural frequency of your system, you go up on your SRS curve, find that acceleration, and then run a G-load analysis. So that's all you do. So how is a shock response curve generated? Well, it's generated from this system right here to the left. You have a base input, and then you have a damping factor, and then a spring constant for a single degree of freedom system, and then you have an output. So just applying the simple equilibrium equations, you can derive the differential equation you need to derive a SRS curve. So this is that system to the right. Next, it's not real practical to work in this form right here in differential equation form. It's more practical in programming to determine a transfer function. So you have to go to the Laplace domain. So once you're in the Laplace domain, you rearrange this equation so that you get a transfer function in the form of your output over your input. And so you can derive a transfer function as shown here to the right for the system right here to the left. Now to convert that to terms of acceleration, because in reality you're dealing with shock pulses in terms of acceleration, and you're really wanting an acceleration output so you can get G's, you multiply it by S to take the derivative. In this case, I'm going from displacement to acceleration, so I multiply by S squared, and you can see these terms cancel, so you end up with the same transfer function. But just to be mathematically sound, that's how the transfer function is derived. Now, once you have your transfer function, you want to put it in terms that's meaningful for you. In this case, damping ratio, spring constant, mass isn't real practical. It's nothing you can really work with there. So now you got to go find some other equations and then put it in the form that you want it in. In this case, for an SRS curve, you want it in the form of the natural frequency of the system and an amplification factor. So just using simple algebraic manipulation, you can formulate this equation right here. And this is the transfer function we'll be using in our programming aspect of this lesson. So once you have your transfer function, now you can begin to derive your SRS curve. So what do you do next? You supply a shock pulse. It could be any shock pulse. It could be a half sine, sawtooth, whatever. In this case, I'm inputting a half sine 11 millisecond 20G shock pulse. I run it through my transfer function. I specify a natural frequency and an amplification factor, and then I get a response curve. From this response curve, what's important is the max absolute value of your response. In this case, it happens to be just north of 30 G's. I want to store that, and then I want to run several different frequencies. Just change the natural frequency and then get the peak response and then plot them. So then I plot the peak acceleration responses versus the natural frequencies, and then you have your SRS curve. So it's that simple. So now we're going to step into the Python programming to show how simple it is to derive an SRS curve for any given shock pulse. To generate an SRS curve in Python, some packages you're going to have to import include SciPy, NumPy, Matplotlib. Once you do that, basically have all you need to generate an SRS curve. So now I have some inputs. I have a test frequency, and then I specified my amplification factor that I'm going to use across all frequencies, and then I have my simulation time. I'm going to simulate across 6 milliseconds. Basically, I'm going to use 1000 points between 0 and 0.06 milliseconds, and then I have my frequency band over which I'm determining my peak accelerations from, and I'm going to choose 200 points between those 1 and 1000. Next, I create my transfer function. Okay, I assign it to z, a variable z. So this comes from the SciPy package. Basically, it's going to just that uses that equation, that transfer function that is given in the slide deck. It's going to be your output over your input. And then next I generate my input curve. In this case I'm generating a half sine pulse. So I have my amplitude in G's of 20. I want my half sine period to be 11 milliseconds, and then I have a function where I calculate basically the sine wave across that time step that I'm specifying with that given amplitude. So I will get a sine function, a sine wave, but I really just want a half sine pulse. So for every time beyond that half sine period, I assign the function a value of 0, and then I plot it so to make sure it looks right. And yes, it looks right. I have my half sine pulse, and then everything after that is 0, just like I wanted. So next, what I do is I run my simulation. So I pass the input into the transfer function, and you do that with the LSIM function, and you get your time output, your response, and then your input. So now I want to plot my response and make sure I'm capturing the fidelity I need. So I plot the response for the transfer function specified with a natural frequency of 80 Hertz, and it looks like I captured the fidelity I needed. So I think that's good. So now I find, and once I have realized that my response curve has got the fidelity it needs, then I go ahead and run different natural frequencies through that transfer function. And so that's what I do here is I specified my natural frequencies I want to calculate my response from, and then I create a list where I'm going to store my peak accelerations, and then I run, just basically loop through and determine my peak response for the different natural frequencies. Once I have that, then I plot my natural frequency versus my peak responses, and then I generate my SRS curve as shown here. So now what I can do next is I can change my input. Instead of having 20 G's, maybe I want it 50 G's. Run this. Still have enough fidelity. And then I run it, and then I get a different SRS curve. So you can see my SRS curve changed a little bit. It may make more sense if you plot it instead of log, you just plot it on a linear scale. You can see that basically I put in a 50 G half sine, and I could see up to just north of 80 G's response. So that's how you generate an SRS curve in Python. It's really pretty simple. So guys, that's it. That's all I got for today. I'll see you next time. Adios.